Now we are going to talk about, in the previous video we talked about the Fermi level in case of pure semiconductor, in case of an intrinsic semiconductor. Now we'll be talking about this Fermi, the concept of Fermi level for extrinsic semiconductor. So Fermi level for extrinsic semiconductor. Now, as we understand that we have two types of extrinsic semiconductors, one is p-type and another is n-type. So first we will discuss this Fermi level in case of n-type semiconductor. So, as we understand that if I go with the energy band diagram for this kind of situation, we have a valence band and we have the conduction band. So this is conduction band. Okay, this is the energy axis. And so this is my conduction band. So what happens? The donor impurity that is added to this intrinsic semiconductor, it is just below this conduction band. This donor level is I can draw this. So there is an additional level. As we go with doping this pure semiconductor with a pentavalent impurity, we are going to have the energy level for that, for all of those atoms, so that will be E donor. Now, as this distance is very small, I mean, because we understand the conditions for doping, so this distance between conduction band and donor energy band is very small. Even at room temperature, almost all the electrons that will be in this donor level, all these extra electrons from this donor impurity atoms, they will jump into the conduction band. Now, the probability of occupancy of energy level by the electrons towards this conduction band is certainly more instead of the valence band, and it can be understood by the closeliness of this the electrons that are close to the conduction band. So the probability of these electrons to be in conduction band is large. So that's why we say that in n-type materials, the Fermi level EF, it gets shifted towards the conduction band. So that could be the reasons. Okay, so this is my Fermi energy, and this Fermi energy is towards the conduction band when we have n-type of semiconductor. Now, if I talk about the occupancy, say n I take, this occupancy will be nearly equal to the number of electrons at the donor level. So this should be kept in mind, and we can have the distribution, Fermi-Dirac distribution function for this situation. So if I take n as the number density, so this is Nc e to the power of minus EF minus EC divided by kBT. So this equation is, we already understand that this equation comes from Fermi-Dirac statistics, right? This gives us the number occupancy of the electrons. So here this n is closely equal to Nd. So as I have proposed this approximation here, So I can use this n for this n. So what am I going to get is nd equals nce to the power of minus ef minus ec by kbt. Now we can have more simplifications. This nd by nc is e to the power of minus times ef minus ec by kbt. Now we can apply log. So applying log on both sides, we will have minus times ef. Okay, sorry, here is a correction. It is not minus, it's plus. It has to be plus. So it's plus. So this is ef minus ec by kbt is equal to log of nd by nc. That should be the case here. I think it's clear up to this level, and we can have the expression for Fermi energy from this equation. And what will be that? So that will be ef is equal to, that will be ec okay, so this is ef. I have ef here. So ef is going to be ec, minus kbt log of n c by nd. So this equation gives me the position of the Fermi energy in case of n-type semiconductor, and its value comes out of solving this equation. We can have the position of this Fermi energy in case of n-type extrinsic semiconductor. Now, if I proceed the same thing for p-type semiconductor, extrinsic semiconductor. So if I continue with Fermi level for p-type semiconductor, and now in this case we better understand that we add the trivalent impurities to the semiconductors, to the intrinsic semiconductor, and we are able to develop holes in the valence band. And in this case, if I go with the energy band diagram, this is my valence band, this is my conduction band, and in this case we have the acceptor impurity, and that acceptor impurity is close to the valence band. So I'll call this EA, and this is perfectly EV, and here we have EC, and this is all about energy. All right, and we can see here this is the energy gap. This whole thing is the energy gap. Right? Now, in p-type materials, acceptor impurity is added just above the valence band. Okay, due to this, large number of holes get generated in the valence band, and at room temperature, the electrons from valence band jump to the acceptor energy levels. Right? So electrons from this valence band they jump to the acceptor energy level, leaving behind a hole, a positively charged vacancy. So leaving behind a hole in the valence band. So this certainly shifts the position of Fermi level. This shifts the Fermi level towards the valence band. So in this case, we have Fermi level EF, and that EF is shifted towards the valence band. Right? Now, if we have to go with same analysis here, we can think of holes. Suppose we have H holes. So these H holes will give us will be nearly equal to the number density of acceptor level. That will be the case. So I can immediately think of this Na equal to Nv e to the power of minus EF minus EV by kBt. Okay, so we have written down the Fermi-Dirac distribution for this situation. So it starts from EF and it ends at EV. In the previous case, it starts at conduction band and it ends at the Fermi level in case of N-type semiconductor. So if we proceed from here, what we will have Na by Nv. So our job now is to find an expression for the position of this Fermi level in case of a p-type semiconductor. So this will be e to the power of minus Ef minus Ev by kBt. There should be no problem with this. So I can write log of Na by Nv equals minus times Ef minus Ev divided by kBt. That should be clear. And this kBt will come here. So this is kBt log of Na by Nv equals minus Ef plus Ev. Now in this case, we will have Ef, the Fermi energy will be, okay, if I transform it here, so it will be Ev, and I transform it back here, it will be minus times kBt log of Na by Nv. So this gives me the final expression for the Fermi energy in case of p-type semiconductor, and we can better understand that in this case we have the acceptor level because we are doping the pure semiconductor with a trivalent impurity, and this trivalent impurity generates holes, right? And these holes are created by the at room temperature. These holes are created in the valence band, and electrons jump to the nearest acceptor level. So this is how conduction takes place when we apply the external potential difference to this material. So this is the expression for Fermi energy for p-type semiconductor.